Okay, we're gonna start modeling our gable frame because this is the first part. So I am teaching you right now on how we will model the gable frame in ETABS. So our gable frame has this. Okay, this is the perspective of our gable frame, and this is the elevation. So as you can see, the ridge height is 16.5 and the eave height is 11.5. And this is our plan. So we have 30 by 36. So if it is wind normal to the ridge, it is 30 by 36. 30 ang L, ang 36 R is B. So let's go to ETABS. No? So open your ETABS, then just select metric and United States. Then just hit OK. Now since it is 30, no? As you can see here, it's A, B, C. So 3. So it's 3. 3 grid lines, and in y direction it's 7 grid lines, so 7 grid lines. And for the spacing of x direction, that is 15 15, so put here 15 meters. And on the y direction, I think that's 6 meters. So our height, story height, okay, 6 meters, right? Okay. So our height is, we have 3-story, first ground floor, second, third, so we have 3 stories, or I think 2 stories only. So the eve height is 11.5 and 16.5. So just click the story data and just, I think, delete this one. Delete story. Then our first is 11.5. Then finally it's 16.5. Okay. Let's try. Then hit OK. So the very first thing we do is define the properties. So first, the properties we should define. If in the future video, I will show you how to do automatic wind loading. So just click add new property, then auto select list. So in this auto select list, just rename it as auto underscore say beam and column. So this is for the beam and column. For, or just click auto tapos wide flange. So you want wide flange, then it's wide flange. So anything that you use wide flange. So I think let's start with 360. So 360 mm up to, I think, 690 is enough. So that's very big. Okay, that's 360. So we add. So as you can see here, are the range of our steel sections for wide flange is 360 up to 690. Then okay. Then another is for the bracing. We try to first, since we don't have bracing, or we don't have hollow steel section or HSS, then we should import properties. Like for example, we tried to use pipe sections. So pipe sections, we have this one. So for 42, that is almost 3/4. So 3/4. No, it's almost 2 inch. 2 inch. So I think it start with 48, 2 inch up to um 5 inch. So 127. Anyway, it's 48 mm up to 127 mm. So let's import that. Then again, we add new property and select this auto select list. Then you take here is auto HSS pipe, because it's a pipe. It's a circular pipe. Then just uh, select those HSS pipe and just add. Okay. Then okay. Now since we have defined our frame, we need to define our cladding. But this cladding is not gonna be designed, no? So we will not put any purlins here or girts, because that is for components and cladding. We, in this lecture, we will focus on MWFRS. So that is what we are discussing, especially in the pressure coefficient, or the external pressure coefficient for enclosed and partially enclosed. So but we need the cladding, or we need the, yes, the cladding or the covering, because that is where we shall apply the CP, because we will use the not the other loading. What do you call that load pattern? Just try wind. Instead of using extend to the diaphragms, we try to exposure from frame and shell object. So we gonna use the shell object. So that is the thing that we gonna put our, you call that, our wind load. So first we try to define the slab section. This we call this as roofing, or the metal corrugated roofing, etc. So anyway, this is just for modeling. So for the next video, we will try to put the load cases and load pattern. So first, we add new property. Let's call this one as say cladding, then roof, then anything slab material. It's okay if it's 4,000 psi or any. So this doesn't really matter, because in our modifiers we will try to remove all the weight and what you call that, the bending strength and etc. So anyway, instead of modeling it as a shell tin, just model it as a membrane, because the difference between membrane and shells is that in the membrane, when it is applied, when load is applied to the membrane, most of the it will not resist the loading. So therefore, this membrane will transfer 100% all of the loads to the MWFRS. So anyway, we don't have purlins or girts here. We try to immediately transfer the loads from the membrane directly into the MWFRS, instead of membrane into the purlins or girts or the components, but it's membrane directly to the MWFRS. So if we use shell tin or shell thick, there is still a resistance for the loading. So it's not almost 100% transfer of load to the MWFRS. So we model it as a membrane. So don't forget that we model it as a membrane. So uh, if we don't want to consider the stiffness modifiers or the strength or the resistance modifiers of this slab property, or this slab or this cladding roof, meaning it will not resist any of the loading, we just try to make this as zero, especially in the membranes or anything, just put it to zero, including its mass. So we just try to apply dead load later in the video, in later videos. Okay, so just make it all zero. So it's just anything, it's slab or just try slab, no? So review them again. It's zero. Okay, then okay, then okay, then we should also define wall sections. So same thing we do. uh, we try to cladding wall to make this as a membrane. Then the modifiers, let's try to make this zero, so that anything, it's just an envelope, it's just a shell. It doesn't really provide strength, or it doesn't really provide stiffness to the entire structure. Thus, our MWFRS is frame only, is a frame only. So okay, then we apply okay, then okay. So we have defined the frame and the shell, in which in the shell, the purpose of that one is for the loading. So because the loading or the wind loading is pressure, no? So we need to, it's an area. So anyway, let's go to start modeling it. So go to the elevation, I think elevation 1. So this is the front view. So you can see this is elevation 1. So we will see this front view. So first we go to elevation 1, then apply. Okay. Now, is this right? Is this right? Let's review our grid system. Hmm. I think it's our story is so high. So modify shows. Okay, I'm sorry. This should be 5, and the total elevation should be 16.5. So okay. So just review your elevation. Okay. Okay. Okay, now it's okay. Now we try to put our first column, then select the wide flange. Okay, this is our wide flange. Our column is this one. Okay, sorry. So let's try to put the column. Okay, then uh, another column here. So next is our beam. Okay. Now, let's try to see if the orientation of our column is right. So we just try to see it as in plan view. Anything anyway, it's story of life. So as you can see, our orientation is this one. So the if we have a loading in x direction or lateral load in x direction, uh, this orientation will bend in its major axis. So this is correct. This is the correct orientation of the column. So anyway, let's try to finish our um, so as you can see here in this 3D view, you can see our partial frame. So this is our first frame. Then let's try to make other parts. So first we try to see the what you call this one A elevation air, or what we call as left side elevation. Okay. So let's try to apply this one. Apply. Okay, our left side elevation, I think is this right? Okay. Then we apply wide flange over here. So that is one there. And let's try to do this. Let's try to break this okay, if you want to see this one as something that is, just click extrusion, no? Just click extruded view. Okay. Then next, we try to split this one. So we try to split this one and also this one, this what we call that, this column. Let's try to split. So edit, then try to split the frames. We just try to divide it into, I think, 2. So 11.5 divided by 2, that is almost 5 meters. So anyway, let's just run this again if there is a problem in slenderness ratio. But I think 5.75 is enough for something like almost 460 mm wide flange for. Anyway, just divide it into 2. So later we'll gonna see in later videos. But the goal of this whole wind loading playlist on my YouTube is for us to know the moments, or the moments, the shears, and especially the story displacement, story shear or story forces, and the overturning moment. So anyway, we are not really focusing on designing here. We just want to see the shear and moment diagram, the axial diagram, etc. So um, let's just try. Let's just try. So we have split here. Then let's try to put again here. Okay. Okay, then let's go to elevation B. Just click here, guys. Just click the move up in list. So elevation B. So elevation B is here at the ridge. So we try to put here. Okay. Sorry. Elevation B is not. Sorry. Okay. Here is the ridge. Okay. So just make sure it's still auto wide flange, no? Our definition for our frame. So as you can see here, we have a wide flange here, wide flange there. Okay. Then finally in the last elevation C, or what we call the right side elevation, let's put um, there one. And if you didn't split here, you cannot put uh, wide flange in the middle of the column. So in the mid height of the column. So just okay. Okay. What's happening here? I can't seem to find this. Okay, so that's one. Then just delete this one. Just delete. So we delete our column so that it will have a unified. Ano. So anyway, it's just my one of my because it's much easier. Okay. Then okay. Now let's try to replicate it until at the back. So edit. So first select all. You can see I selected all. So select all of the elements. Then edit. Then try to replicate. So okay, replicate. So our replication is this. We have 6 meters spacing, and we have almost seven. No, first one, two, three. So six. So six replications and almost seven frames all in all. So one per the horizontal vertical grid or the Y grid. So okay, so we have seven grids at Y direction. So click apply. So you can see we have here. Then okay, so we have here some of the elements, excess elements. So we remove the excess part. Then check your structure. Then next, we try to put some bracing because just try to put some bracing. No? So I think it's elevation A, apply. Okay. So our bracing here is the auto pipe. So that is our bracing. So bracing. I think it's enough. Maybe. I so sorry. I'm very sorry. Okay. So the purpose of this bracing is for the loads, especially at the you call that at the roof to transfer the lateral load into the up to the foundation. So let's try inputting this one here, then there, then so just try. So anyway, if it is a problem with the slenderness, then we just adjust it, but it's not the topic of our of this video. It's about inputting wind load and determining the shear and moment and the actual load, actual diagram, shear and moment diagram, etc., and the whole structure. So anyway, if there is a problem with story displacements and story forces, then we can just try to revise this structure, this model. As you can see, this is very long, no? Our geometry is, the length is 16 meters. So obviously, this will cause buckling or slenderness if this type of element will, um, what do you call that? Is loaded in with compression. So anyway, let's just try. Then we try here also the back. So okay, then here. So you just forward the videos, no? I don't have time editing this one. Then let's go to C. So I will finish later the for the roofing part. So anyway, so this is just for the transferring of load from the topmost part of your structure into the foundation. This is what we call a load path. So anyway, this is obvious or the basic load pathing. So next, here we try to uh, put braces on the outer edge because it's much better to put bracing at the outer part than in the middle. So anyway, this is just for purposes of introducing to you how we can get the shear and moment diagram, because this shear and moment diagram is what we need, or the actual diagram is what we need in designing steel structures. So finally we have this one. Okay, now for the shells, we try putting for the shell. So first, let's try the wall. So elevation 1. So it's the same thing, but this is not replicating. So first of all, select. So select all this one, or you just drag them and select. But you will also select the joint. So just select here. Anyway, this is extrusion, extrude, extrude frame. So I have selected 4 frames, and I will extrude the shells. So the shells that I will extrude is both for the wall and the roof, and this is for the side and the roof. No, it's if it's the wind is parallel to the or normal to the ridge, the wall here is for the windward and leeward wall, so this is not the side walls. But if the wind is parallel to the ridge, so you can remember, this is what we call side wall. This is side wall. But if it is normal, this is leeward and windward, or windward leeward. Okay. So same. But if we want for a single shell throughout the whole structure, we just try to extrude it for the whole length, or the yes, the whole length. The whole length is 36. Okay, or B if it is wind normal to the ridge. Okay, then also only one. Then let's try to apply. Now we have this one. So obviously um, we have different walls. So instead of slab, we will try to put wall cladding, or cladding wall. So select the two edge shells. So you can see if you have selected two shells, it will highlight two shells. Then assign for this is wall, for the wall. Then try to select shell, then wall section. Then we apply the cladding wall we defined earlier. So apply. Okay, cladding wall. So we have, you can also see here it will say cladding wall. So our next definition for our shell is the shell in the roof. So select the two shells at the roof. Sorry. Not. So we have selected the two shells. You can see here it's two shells. Then assign the slab section, because this we have defined it in slab. So cladding roof. Okay, so if you want to review, just modify show properties and see it is a membrane, then it's all 0. So anyway, okay, then let's try to apply. Okay, then apply. Okay, now for the front or side walls, if it is the wind normal to the ridge, so just select this one. Okay, just select this one, then select wall. Instead of wall, select cladding wall, then drag it here. So, sorry. So, select again here, select the draw rectangular flow plan, for plan, then just drag it, then up to here. So, we have that one. Then, for the triangular part, just select this draw floor plan. So, do this one, and finally, this one. Okay, now for the final part here in the elevation 7 at the back. So although in my perspective view, I have an opening here. Let's just try to because this is example of a hangar, no? Example of a hangar that is a garage for airplanes, no? Since I have an opening, I'll just try to model it as an enclosed. Then let's check if it is partially enclosed or enclosed. Because if it's partially enclosed, we could use the 0.55 plus and minus 0.55. But as you can see here, this is a partially enclosed because we have in a parallel, no? If loading parallel to the ridge, if it is coming from the top to bottom or coming from here, no, from this one to this part, um, you can see that this is a positive wall. Then obviously this is very big. The opening here is very big, and I I think this will be classified as partially enclosed, but we can see it later, no. So anyway, this is just for the modeling. So as you can see here, we turn that again. Then we go to elevation 7. That is the very last, or the at the back. So again, we try to do this one, and okay. Okay. So we have everything. We have all it covered. Our whole structure is covered. So let's X this one or close that one. Then we try to remove the axis. Then we try to see the axis of every shell. So this is a shell, shell, and shell. We try to see their axis. So unfortunately, the slab part, we cannot rotate that axis. So we must have every direction must be uniform. So if our z-axis or the local z-axis of our shell is pointing outside, then all of them should be pointing outside. And since it is pointing outside, then the positive part now is the suction. So our CP, if it is suction, we use it as we change their signs. So suction now becomes positive. So to know what I'm talking about, then just select view, then select this set display options, then go to object assignments, then apply local stiffness, local axis. So apply. Okay. So you can see here we have the axis of the local axis of every shell. Now we have some shells here that is not the same with other shells. And as you can see, as I'm talking about, I cannot flip this slab. So um, the roof is pointing outwards. As you can see, just focus on the color blue. That is the z-axis. That is the local z-axis, or that is the axis perpendicular to the shell. Because that is how wind loading is. Wind loading is perpendicularly applied to the shell. Okay. So you can see here, I cannot, as you can see, edit, I cannot reverse the axis. It's only for wall. So therefore, we shall make all the walls that is not to the direction of going outside. So this one, this is not this the local z-axis of this shell is not pointing outwards, or say the direction of the suction. So we apply edit, then edit shells, then reverse wall local axis 3 or local 3 axis. So now we have this shell is now the same with other shells, but I think we have some shells also that is not pointing. Let's see this one. It's not also pointing. Then edit shells, then reverse. So now this shell is its local z-axis pointing outside, or it is now in the suction. Or the positive part of this one is in the suction. Then try to find other part. So okay, this one, this one. So as you can see, this one, it's pointing inside. So we try to flip it because this will be okay. Now, as you can see here, all of the structure is all of the shell is pointing outside, or the local z-axis of the shell is pointing outside. So we have a uniform direction for all local z-axis, and that is pointing outside. So anyway, the local y and x-axis doesn't really matter because as I have said earlier, wind loading is always perpendicular to the shell. So our next video is about inputting the load cases and load patterns. And as you can see here, for this video, I will show you how to know what is the fundamental frequency of the structure. So click analyze. So click analyze, then try to see the set load cases to run. Then do not run this dead load, and live load, do not run this. So only run the modal analysis part. So this is the modal analysis. So let's try to run. So therefore we can know. Let's try to save it. So Gable 30 by 36. Okay, we try to okay 30 by 16.5. The 16.5 is the ridge. So we save. Now it will try to run. Then think it's okay, it's finished. Okay, then let's try to see the tables here. Analysis results, structure output, and model information. So as you can see here, click the model periods and frequencies, show table. The model frequency is 0.993. That is less than 1. So I think we can try to use the um, since this is a flexible building, we try to use the formula, but obviously I think this will be almost 0.85 also. But we can try to see this one as rigid. So here, so this is a rigid frame, okay? But if I'll add, no? I'll add. So let's try. If I'll add other braces here, it will be, I think, okay, it will be flexible. So anyway, that is it, no? For the next video, because I will not try to continue this one because it will give me a higher video length. So stop recording.